case of extended objects, and we considered in fact the elastic scattering of the electrons on hadrons like proton, and then we said in the case of elastic scattering, EN scattering, electron nucleon scattering, in particular we can consider electron proton scattering, the differential cross section can be written as the differential cross section corresponding to a point particle scattering without the nuclear spin effect, times and the recoil effect of the electron has to, of the proton has to be added to this, 2e over m sin square theta by 2 in the denominator, times the charge and charge distribution and the electromagnetic interaction part. So, the magnetic interaction part, which is for a point particle would correspond to the magnetic dipole interaction. Here, in the case of particles which are not point particles, we will have to consider form factors. So, there are two form factors, one is the electric form factor and magnetic form factor, and they appear in the expression for the differential cross section in this fashion, plus 2 tau g m square tan square theta by 2, where theta tau is equal to q square over 4 m square c square, where q square is equal to minus q square, and q itself is basically the form momentum transfer. So, P corresponds to the initial momentum, energy and momentum of electron P, and P prime is the final momentum of the electron. This we discussed yesterday, and we also discussed that in the case of high energy electrons, high energy electron beams, there are we have seen E P not just elastically scattering to E P, but can go to some E x other particles. X could in general be any number of hadrons. So, in one particular case we saw P, the proton itself, and pion in that, or in general it could be any different hadrons, A, B, C, etc. are hadrons, either mesons or baryons. So, this is inelastic scattering. Such inelastic scattering let us represent in fashion as E minus in the initial state and E minus in the final state, and proton in the initial state, but going into different hadrons in the final state, right. So, I can picturize it in this fashion. We already said that the effect of electron interaction with proton can be picturized in terms of exchange of photons, and that is what we have here. Now, let us look at this inelastic case and then see what are the changes that we had to make. The earlier formula that we had here is basically the called the Rosenbluth formula, and G E and G M are the electric and magnetic form factors which depend on q square. So, we take in the case of inelastic case, we consider an expression similar to that of the Rosenblatt's formula and write it as d omega d sigma over d square sigma over d omega d e prime. One difference here compared to the earlier elastic case is that we are also differentiating it with respect to or taking a different varying the final electron energy. If you remember our earlier discussion, we had said that in the elastic case, the final energy of the electron is fixed. You get a particular value for the electron, and if you look at the experimental spectrum, you indeed get a large number of points at E prime is equal to whatever the kinematically allowed value, a fixed value. But in the case of inelastic collisions, this electron transfers the energy, some of the energy to the other particles, and then the energy of the electron, because the way it goes x, if you look at the earlier expression, earlier picture, E p going to E x, x need not be a particular particle, right? It can be many different hadrons. In that case, the energy of the electron will not be fixed. It will vary depending on what are the other particles, what their masses are and what their energies are, etc. So, we will get an energy distribution for the electron in the final state. So, therefore, we can consider the electron energy spectrum and see that it will now depend on form factors similar to the earlier case, but the expression is similar to the earlier case, but earlier case of elastic scattering, but the structure, the form factors are now slightly different. They are called actually the structure functions, and they will be usually written as W2 q square nu, W1 q square nu, functions of q square nu, q square and nu. I will tell you what nu is in a moment, times tan square theta by 2. The theta dependence is similar, the same. There is a term which does not depend on theta square, and there is a term which depends on tan square theta by 2. In addition to that, of course, d sigma over d omega mod has some theta dependence, but apart from the mode scattering differential cross section, which corresponds to the point like particle without the spin considered in it inside this one, spin of the target which is considered in it, or without the magnetic interaction. Okay. So, this structure function, these W1 and W2 are called the structure functions, and there is no recoil factor that we will consider in these cases, because there is no final proton that we are, it is not the elastic scattering that we are considering. It is an inelastic scattering that we are considering, and nu itself is basically E minus E prime, and q square of course is similar to the earlier case, p minus p prime square. So, in addition to the q square, the E minus E prime is another variable which can independently vary compared to q square. Let us see how that goes. Okay. So, the difference therefore is that compared to the earlier case is that the structure functions are now functions of not only q square, but also nu, which is basically the difference in the energy of the final and initial electron. So, let us look at why that nu is now not an independent variable, unlike in the case of elastic case. So, let us consider in the elastic case first, elastic scattering, say E p going to E p. Let me denote the momenta as P e for the initial electron, P p for the final electron, and P prime for the initial electron, final electron, and P p prime for the final proton. In these are 4 momenta, which means that the first or the 0th component is energy of the electron, in fact E by c, and the 3 momenta, and P prime similarly is E prime over c P E prime, okay, and P P is at rest initially. So, it only has the mass of the proton and no 3 momentum. P P prime is, let us say, some E P prime and P P prime. All right. So, energy momentum conservation will tell you that the 4 momenta, addition of the 4 momentum in the initial case is equal to P E prime plus P P prime, the sum of the final momentum square. This includes both energy conservation and momentum conservation. 0th component will give you the energy conservation, and the 1, 2, 3 components will give you the momentum conservation. Now, let me write it in a different way. P P prime is equal to P E minus P E prime plus P P. So, if I square this, P P prime square is equal to, what is there in this bracket is basically q. So, it is q square plus P P square plus P q times P P. This is essentially equal to left hand side is mass of the proton square. The 4 momentum square is equal to the mass square, which we saw yesterday. Okay, let me actually write it again. So, this is equal to E P square, E P by c, in fact, E P square by c square minus P P prime square is equal to q square plus, similarly, this only has the P P only has the 0th component, which is m square c square, plus q dot P P. So, there is only the 0th component. So, here q is basically E minus E prime into, so this is twice this thing. So, 2 times this into mass into c, and this is m square c square energy momentum relation. M is the proton mass, is equal to q square plus m square c square plus 2 nu, E minus E prime I denote by nu, and m c. Okay. This tells you that q square E by c there is. So, m square cancels with the m square on the left hand side, and then this will give you the relation that 2 m nu is equal to minus q square. So, nu is not independent of q square. Given q square, nu is given by minus q square by 2 m. So, in the elastic case, these are not two independent variables. But now, for the inelastic case, let us consider the example of E p going to E p pi 0, right. So, now you will see that the invariant mass, okay, let me write down the 4 momentum conservation, P P P is equal to P E prime plus P P prime plus P pi 0 prime, where P pi 0 prime is the momentum of the final pi 0 and rest of it is similar to the earlier case. So, here again when we consider p p prime plus p pi 0 prime square, this is what we call the invariant mass of the system. This is equal to W square C square invariant mass of p pi 0 system. So, this tells you that W square C square is equal to P E minus P E prime plus P P square, which is exactly what we had earlier on the right hand side, which is q square plus m square c square plus 2 m nu. Since W square c square is always larger than m square c square, because it is the sum of p prime p p prime plus p pi 0 p prime square, which means p p prime, that is the form momentum of the final proton square itself is m c square or m square c square, and in addition to that you have the part coming from pions momentum for momentum. So, W square c square is always larger than p square c square, and along with this, so therefore, that will give you that the right hand side q square plus 2 m nu cannot now be 0, it can be, it has to be always larger than 0 in this case. And there is no such relation, and there is no such relation between q square and nu as we had in the case of elastic collisions. Okay? In the elastic collision case, it was actually q square, W was replaced by m p, the mass of the proton. So, we had q square plus 2 m nu exactly equal to 0. Here it is not so. So, these two can, q square and nu can vary independent of each other. All right. So, this is why we have the, in the expression for differential cross section in the case of inelastic scattering, the form factors or the structure functions as they are called are functions of two variables q square and nu, unlike in the case of elastic collisions, elastic scattering, where it is only a function of q square and nu is not independent of q square there. Now, usually we can actually write the variable nu in a different fashion, or nu and q square in a different fashion. We can actually trade it to, or trade it with a variable x, which is dimensionless. Nu is E minus E prime. So, the dimension of nu is dimensions of energy, but we can define a variable called x as q square over 2 m nu. From now on, we will consider capital Q square instead of small q square, because we saw that nu is equal to minus q square over 2 m in the elastic case, and nu is E minus E prime. Usually the electron gives energy to the proton, and therefore, the energy of the final electron is always smaller than the energy of the initial electron. So, E minus E prime is positive, nu is positive, and q square is always negative. So, minus q square is taken as a positive quantity q, capital Q square. And elastic scattering, gives x therefore equal to 1. For inelastic scattering, we have 2m nu minus q square is larger than 0. So, that is equal to, or that is equivalent to 2m nu 1 minus x larger than 0. That tells you that x has to be less than 1, because m is always positive, nu is always positive, therefore, x is always less than 1, and minimum value of x is 0, where q square is 0. So, that gives the range of x as 0, between 0 and 1. So, these are the two variables that we should consider, q square and nu, or x and q square. Now, consider let us have a summary, the three different cases we had for point particle case. D sigma over d omega equal to d sigma over d omega mod times 1 plus now q square divided by 2 m square c square tan square theta by 2, and elastic scattering case, the Rosenbluth formula d sigma over d omega equal to d sigma over d omega mod times g e square plus tau g m square over 1 plus tau plus 2 tau g m square tan square theta by 2, where tau is q square over 4 m square c square. And inelastic case, we have now E prime not fixed. So, therefore, we consider d square d omega d E prime, where E prime is the energy of the final electron, equal to d sigma over d omega mod times W 2 q square nu plus twice W 1 q square nu tan square theta by 2. If you look at these expressions, you see that G E and G M are dimensionless, and because the d sigma over d omega and d sigma over d omega mod both have the same dimensions, whereas W 2 and W 1 have dimensions of 1 over energy, because on the left hand side we have d square sigma over d omega d E prime. Okay. So, there is a 1 over these structure functions are dimensionless, have dimensions of inverse dimensions of energy. Now, let us take actually the inelastic scattering case as kind of a general expression. Supposing this is the general case. So, the expression is written in terms of W 1 and W 2 in the general case, then W's in the elastic and inelastic cases can be considered in this fashion. Let us consider the elastic scattering case, not point like particle, but particles like protons with extended charge distribution and composite particle, or compositeness itself is not coming in here, the extended particle, not point like particles. we will consider an assumption that assume that GE is equal to GM, just to illustrate this and make it a simple case. So, GE is equal to GM and denote it by some common G. In that case, if you compare these expressions, Rosenblatt and the inelastic case expressions, then you can see that W1, let me denote it by W1 elastic, corresponds to Q square over 4 m square C square into G square into delta nu minus Q square over 2m. You remember the elastic case, nu is always equal to Q square over 2m. So, that is what we have done. We have taken this expression and that 1 over 1 plus tau in the Rosenblatt expression, say here, is cancelled by the 1 plus tau times G E square coming from the numerator when G is equal to Gm. And then W2 elastic is equal to G square delta nu minus Q square over 2m. This is because G E square plus tau G m square over 1 plus tau is essentially equal to G, 1 plus tau cancels. Okay. Now, this is one thing, and G square is a function of Q square. Okay. So, we have this expression here, keep that in mind, and let us go to the case of point particle scattering. Then W1 point particle is equal to Q square over 2m, sorry, Q square over 4 m square C square delta nu minus Q square over 2m. And W2 is just delta nu minus Q square over 2m. In terms of the dimensionless quantity, m C square W1 point is equal to Q square over 2 m nu delta 1 minus Q square over 2 m nu. Using the property of the delta function that delta A x is equal to 1 over mod A delta x. This is the property of the delta function, which can be easily verified. This gives you 2 m C square W1 point is equal to, this is nothing but x delta 1 minus x. And similarly, you have W2 point particle is equal to 1 over nu 1 minus delta 1 minus x, or I can write this as nu times W2 point is equal to delta 1 minus x. Why are we doing this exercise? What we are saying is that if you look at this inelastic scattering expression, d square sigma over d omega d e prime in terms of W1 and W2, the structure functions, and the mode scattering, then we see that if the particle that it scatters on is point particle, we will essentially see that there is no Q square dependence there in the structure function. It depends only on the dimensionless quantity x. So, there is no particular energy scale associated with this thing. The form factor is not there. It is independent of the energy. You remember our earlier discussions on the form factor. We started with saying that if the particle were not actually, if the charge distribution was not really point like charge distribution, then we will have to consider the charge density not as a delta function, but as some distribution, spatially varying distribution or spatially distributed charge case. In that case, there is a form factor that will come in the expression for cross section, differential cross section, okay, which the form factor itself will now depend on the energy exchange between the electron and the proton. And now, what we are saying is that if it was a point, if it is a point particle, it will not have any energy dependence, which is something which we had discussed earlier. But at this point, what is going on is that if you consider very large energy, very large meaning of the order of 10 GeV etc. for the electron, then the electron may be able to penetrate inside the protons, and then if it sees point like structures there, what we can expect is the scattering with structure functions which do not depend on q square. That is what we have said, right. So, what we expect in the case of, in such cases, for example, if you plot nu W2 as a function of q square for scattering from point like particles or point particles, what we expect is an independent, or what we expect nu W to be an independent function of q square, meaning it is a constant as far as q square is concerned, it is independent of q square. So, if you consider, if you do an experiment and then plot the W2 nu, how do you do that? It is exactly like earlier case. From the theoretical expression model that you have, which is given in the earlier slides, you try to fit to the observed data for various different q square values, and then see that the extracted W2 behaves like this, that is, it is independent of q square. This is the expectation, and indeed experimentally verified this one, okay, which says that when we actually look at large and high energy scattering of the electron on the proton. Okay, so, this is essentially the proton that we are considering. Then electron starts seeing it at high energies, it penetrates the proton, say, it starts seeing the inside structure of the proton, and it looks like there are point like structures on which the electron scatters. Say for example, if you take the picture of proton made of 3 quarks, then you will see that you can imagine that the electron interacts only with a particular quark inside the proton. The other quarks are just spectators in this interaction or spectators of this interaction. In that case, you will see the behavior of this point like particle scattering reflected in the structure functions, behavior of the structure function, which means that nu W2 for example is independent of q square. This is seen by experiments, and therefore, we can infer that there are structures, point like structures inside proton. Okay. So, this indicates point like structure inside the proton. Of course, we will have to investigate a little further and then study a little more to have a better feeling and better understanding of this, and to also confirm that there are these point like particles and they indeed correspond to what we call the quark in the quarks in the quark model, and consistently we can build the picture which agrees with the experimental results. So, we will take on that in the next discussion, taking this further to understand these substructures in a little better way.